What is up, young chemists? Mr. Rosen here. How's it going? Uh, Today we're going to talk about scientific notation, which is a convenient way to write very large or very small numbers. Just going to explain it, and then we're going to do some practice problems, looking at both going from standard notation into scientific notation and also the other way around. All right, so I have just sort of a little example here about scientific notation. So if you want to, you can pause and read it. What it says is the size of the thing that's being measured influences what unit is best to use to represent that measurement. Okay, so if you are measuring, let's say, the mass of a star, okay, and in this problem they talk about Melnick 42, and it's one of the stars in this picture of the Tarantula Nebula, and it's a huge star. Scientists represent its mass using what are called solar masses, and a solar mass is the mass of our sun. So if the mass of the sun is something, if a different star has two solar masses, then it has a mass that's twice the mass of our sun. So Melnick 42 has a mass that's 189 solar masses. That is 189 times the mass of our sun. Now, that number for representing the mass, 189, that's a pretty nice manageable number to work with, right? Representing the mass of that star in grams would look like this. And you could imagine if you were writing a paper or you were doing calculations, writing this number over and over and multiplying by it or dividing by it or having it as part of an equation, that is going to be a real pain, and that's going to be pretty tedious, writing all these zeros out, right? So scientists have a shorthand, sort of convenient way of representing a very large number or a very small number, and that is what's called scientific notation. Okay, scientific notation is a convenient way of writing very big or very small numbers. So how it works it might be a little bit small, so I'll zoom in, but how it works is you start with a number and you have a decimal point, usually over on the right side, and you move the decimal point. Well, if it's a number greater than 1, then the decimal point's on the right side. If it's a number less than 1, then the decimal point's on the left side. But you move the decimal point until you have a number between 1 and 10. Okay, not less than 1, not more than 10. And then that number gets multiplied by 10 raised to some power. And that power is the exponent. So just a little review of exponents. 10 to the 0 is 1. Okay. In fact, that's one of our things here. It says any number to the 0th power equals 1. So that's a big idea. 10 to the first power is 10. And that's our next point here. Any number raised to the first power is equal to that same number. Okay. So if instead of 10, if you had 6, that's a 6 to the 0 power, that's 1. Or if you had 7 to the 0 power, that's 1. If you had 6 to the first power, that would equal 6. And if you had 7 to the first power, that would equal 7. Okay, so any number to the 0th power is 1, and any number to the first power is 6. 6 to the first power is 6, 7 to the first power is 7. If the number is blank, then 1, the exponent will be blank, and then we have a similar situation. So if you're looking at this, the numbers up here, these are all numbers greater than 1. and all of their exponents are positive. These are numbers less than 1, and all of their exponents are negative. Okay, so if the number is greater than 1, the exponent will be positive. If the number is less than 1, the exponent will be negative. So I like thinking about that before I actually solve the problem. I ask myself, is the number more than 1 or less than 1? And that tells me if the exponent is going to be positive or negative. Okay? So let's do some example problems. We're going to go from standard notation to scientific notation first. Okay, so this first number was mentioned in it was mentioned on the previous page. Now, if you want to, you can try to solve these. These are all numbers written in standard notation. We're going to write them in scientific notation. So you can pause the video and try to solve these, although I haven't done any as an example yet. Or you could watch me do the first one and then pause the video and check your answers for the rest of them. All right. So if we were looking at this number, its decimal point would be right here. Now, this is much more than 1. So we know that it's going to be times 10 to some positive exponent. But we have to move the decimal to the left in order to get a number that's between 1 and 10. So if I move the decimal 1, 2, 3 places to the left, then instead of being 46 billion, if the decimal point was right here, it would now become 46 million. So the number got smaller. I moved it 3 places to the left. Now I'm going to move it 1, 2, 3 more places to the left. If the decimal point was right here, our number would be 46,900. So we're getting smaller, but we're not there yet. And I've moved it 3 places and then another 3 places. So 6 places so far. Move it 1, 2, 3 more. Okay, now if the decimal point was right here, at this point I've moved the decimal 9 places to the left. If I put the decimal point right there, that would give me 46.9. Now, is 46.9 a number between 1 and 10? No, it's more than 10. So we actually have to move it another place to right here. If the decimal point's right there, we'd get 4.69. Is that between 1 and 10? Yes. 4.69, that's a number between 1 and 10. Now we're going to take that times 10 to some power. And the power is equal to the number of decimal places that we moved. So we moved 3, 3, 3, and then 1 more. So that's a total of 10 decimal places. Now, this is our answer. But in terms of why it makes sense, 10 to the 9 is a billion, right? 10 to the 9 is a billion. So if you took a billion times 4.69, you would get 4,690 million. But this is 46. So 10 to the 10th power is 10 billion. So 10 billion times 4 is 40 billion, right? And that's, this is 46 billion. So this makes sense. You can always just kind of do that sort of logic check on your work. So this next problem, this is a number less than 1. this number is not between 1 and 10. It's less than 1. So I have to move this decimal point, in this case, to the right until I get a number between 1 and 10. So I can move it 1 place, 2 place, 3, 4, 5, 6, 7. Now if I stopped right there, I moved it 7 places, is 0.641, is that between 1 and 10? No, it's less than 1 still. So I have to go another place right there. If the decimal point is right there, we have 6.41. 6.41. That is a number between 1 and 10. If I went another place, then I would have 64.1, and that is too big. So there's only one correct place for the decimal to be. Now this is going to be times 10 to some exponent. Now I had to move the decimal 1, 2, 3, 4, 5, 6, 7, 8 places. So it might be tempting to say, oh, it's 10 to the 8 because we moved it 8 places, right? Well, 10 to the 8 is 100 million. So if you took 6 times 100 million, you would get about 600 million. Is this number 600 million? No, it's less than 1. So if the number is less than 1, our exponent is going to be negative. So this is to the negative 8th power. You know if the exponent is going to be positive or negative just by looking at the original number and seeing if it is more than 1 or if it is less than 1. So here we have 92,500. We're going to move the decimal point from here to the left. We're going to go 1, 2, 3, 4 places. And that gives us 9.25 times 10 to the 4. 1, 2, 3, 4. And to think about this, 10 to the 3 is 1,000. 10 to the 4 is 10,000. So if you take 10,000 times 9, you get 90,000, right? This is 92,000. So our answer makes sense. Here we have a number less than 1. We have to move the decimal to the right. So 1 place, 2 places. That's 2 places would give us 0.5. That is not a number between 1 and 10. If we move it 3 places, we get 5.03. So 1, 2, 3 places gives us 5.03. Again, you just move the decimal point until you get a number between 1 and 10. Not less than 1, not more than 10. Right? If I move this another decimal point, I would get 50.3. That's too big. So this is going to be times 10 to some power. Again, 1, 2, 3 places we moved it, right? 1, 2, 3 places. So it's tempting to just put a 3 there. 10 to the 3rd power is 1,000. 5 times 1,000 would be 5,000. This number is not 5,000, right? It's less than 1. So we're going to have a negative exponent. It's going to be negative 3. And then here we have this number, which is about 7,243,500. So we're going to move the decimal point to the left. 1, 2, 3, 4, 5, 6 to give us 7.243. Now, because of how many numbers this has, it actually doesn't save us much. It doesn't have too many zeros at the end of it, but this is our number between 1 and 10. And then we say times 10 to some power. And we had to move the decimal 1, 2, 3, 4, 5, 6 places. And this is a number greater than 1. So that's it. And 10 to the 6 is a million, right? 10 to the 6 is a million. So 10 10 to the 6 is a million. A million times 7 is about 7 million, right? Which is what we have here. So these have all been practiced going from standard notation into scientific notation. What I'd like to do is a couple of examples going the opposite direction. This is going from scientific notation to standard notation. So if you want to pause the video and try these, you can. I'm about to work through them. In terms of how you go about solving this, looking at the exponent tells you if the number is going to be more than 1 or less than 1. The fact that this is a negative exponent, it's 10 to the negative 6, means that it's going to be a number less than 1. Now, we have 4.06, and this is to the negative 6. So that's a millionth rather than a million. So you're going to have 0.00. And, if you moved this one place or two places, you would, and then you had 405, you would get there. But we have negative 6. So I'm going to put, I put 1, 2, 3, 4, 5 zeros here, because if I move the decimal 1, 2, 3, 4, 5, and then I had 405, right? If I write this number, this is less than 1, and so that makes sense in terms of my exponents. In order to get a number between 1 and 10, in order to get 4.05, I would have to move this decimal 1, 2, 3, 4, 5, 6, and that's the minus 6. Right? That would give me 4.05. So this is going from scientific notation to standard notation. This is a positive exponent. 10 to the 3 is 1,000. So if you take 3 times 1,000, you're going to get about 3,000. So this should be 3,750. Just kind of looking at that quickly, you could do that math probably. But 10 to the 3 means you're taking this decimal and you're moving it to the right 3 places. 1, 2, 3. So instead of 3.75, if we moved it to the decimal to the right 1 place, we would have 37.5. If we moved it 2 places, we'd have 375. If we moved it 3 places to the right, we would have 3,750. Right? If I took this number and I moved the decimal 1, 2, 3 places, I would get 3.75, and that's times 10 to the 3. This is 3,750, which makes sense, again, because 10 to the 3 is 1,000. 1,000 times 3 would be 3,000. Okay, next one, we have, this is a negative 11 exponent. So this is going to be a small number less than 1. It's going to be 0 point. And just to kind of do like I did in the previous one, if this is negative 11, I'm going to put 10 zeros here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then I'm going to start writing this number, 7, 2, 3, 4. Because I know that that final place is going to be taking me from here to there. So if I check this, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Right? So if I move it 11 places, I get 7.234. And it's a number that's less than 1, so we have a negative exponent. Okay, you can see that writing this number is starting to get a little bit tedious, a little bit of a pain. So the next one, I'm going to slide this up a little bit. This is 5.18 times 10 to the 8th. So 10 to the 6 is a million. 10 to the 7 is 10 million. 10 to the 8 is 100 million. So this is 100 million. If you take 5 times 100 million, you're going to get 500 million, right? And that's about what our answer should look like. We're going to be moving this decimal 8 places to the right. Okay, so if I moved it 1 place, we'd get 51. If I moved it 2 places, we would get 518, and then I would keep on moving it. So if the decimal point was right here, and we moved the decimal 8 places to the left, it would be 1, 2, 3, 4, 5, 6, 7, 8. And that would give us 5.18. We moved it 8 places. So this number, this is 518 million, which is about what we would expect, right? Because 10 to the 8 is 100 million. If you take 100 million times 5, you're going to get 500 million. But again, you can just count your decimal places. 8 places to the left would give you a number between 1 and 10. Last one on here, it's 9.009 times 10 to the 15th. So it's a positive exponent, so that means it's going to be a number greater than 1. We're moving this decimal point 15 places to the right. So 9009. That would be if we move the decimal point 1, 2, 3 places to the right. I actually might have lost count there, but let's see. If this was our number, if the decimal point was here, we would need to move it 15 places to get 9.009. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Ding, 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 ding. So this is the correct number of zeros. If it's helpful, you can put a comma, comma. So the number is 10 to the 15, so that's more than 1. This number is more than 1. We had to move the decimal point 15 places to get a number between 1 and 10. And then in terms of our exponents here, 10 to the 6 is a million. 10 to the 9 is a billion. 10 to the 12 is a trillion. And then 10 to the 15th is a quadrillion, I guess. So right here where this 9 is, that would be a trillion. And so we're another 1,000 times larger than that. Anyhow, this has been a video focusing on scientific notation, going from both standard notation to scientific notation, as well as from scientific notation to standard notation. All right. Keep up the hard work. Practice, practice, practice. Good job. This is Mr. Rosen. I am out.